school we come across various terms, various subjects like science, engineering, technology, and medicine. And there is dilemma. I mean, in your minds also, you think whether I should pursue medicine as career, or science as career, or engineering as career, and so on. So even within science, there are several subjects. There are several subjects uh, like physics, chemistry, biology, but we don't really know meaning of all these terms. So it's important to understand. For example, if I confine to my subject physics, then what is definition of physics? Have you ever, come across this definition in your school days or not? I have talked to many senior students also, but very few of them could really answer this question. So the answer to this question, this contains the history and evolution of physics as a subject. So let us just see what is definition of physics. Definition of physics in a formal manner, physics is defined as science of measurement. Now, this definition itself contains two terms, science and measurement. So we have to define first what is science and what is measurement. So let us go into the definition of what we mean by science, and let us explain what is measurement. Now, science, this is defined as understanding universe in terms of cause and effect. Means whatever phenomena we observe, then what is the cause? And if that is a cause, what effect it produces? So science basically consists of several steps. These steps are, say, the objective description. Means we describe the phenomena which take place in this universe. And what we mean by objective? It means the description depends on the object or the phenomena, and it doesn't depend on the person who is describing that. Now, in our day-to-day life, this is not so. Our description often is not objective. For example, if somebody asks you, or casually we mention that this person is tall or this person is very short. So, this tall and short, it is qualitative. This is not objective description. For example, in a basketball team, a person with 2 meters is short, he is not tall. But a person with 1.7 meter height in a land of pygmies, he will be a giant, he will be tall. So, the description is objective only if it is in terms of some units, some measurements. And this is what science wants, that description must be objective. Description should not be subjective. It should not depend on who is describing, but the description should depend on what is being described. So first step in science is objective description of whatever is happening. Then science aims at establishing cause and effect sequence, that this is the cause and this is the effect. For example, if a body is in motion, then motion is the effect we see. What is the cause behind this? Then the momentum. Body is in motion because it possesses momentum. We see body is suddenly accelerated from state of rest to state of motion. Then what is the reason? The reason is force. There is external force applied on the body and the effect is acceleration. So once we have the objective description, we try to establish what is cause and what is effect. Then we don't stop at that. So once we understand this cause and effect sequence, then we start making predictions that okay, if this is the cause, this will be the effect. For example, we know that if voltage is applied across a resistor, then there will be current flowing. And I establish cause and effect sequence. I find out that ratio of voltage to current is always constant. So I predict that if voltage is doubled, current will also be doubled. If voltage is halved, current will also be halved. This is my prediction. Now, if after making this prediction, I don't stop. If my understanding is correct, then this prediction should come true. Then I go to laboratory, I set up the experiment, and I verify whether the predictions which I have made on basis of my understanding, are these predictions correct? So I verify. If these are verified, then I know that my description, my science, my understanding is correct. And if I find that this verification, it is not verified, whatever I predicted and actual results are different, then I go back. What is the reason for this discrepancy? Maybe my description was not correct. I again go through this loop. I again go to the description. I again revise my understanding and so on. So this is the method of the science. Now we just go into history of science. Whatever I have described, I have defined as science, and you may feel that this is very trivial. This is what just like talking 2 plus 2 equal to 4. So is it like that? So was science like that all the time? The answer is no. Not so long ago, just some 300 years back, science was not like that. But science, so-called science, that is why I have said pseudoscience. In those days, what people called as science, this was dominated not by the scientist, but by the religious leader with backing of the king and the rulers. So combination of religion and technology that helped rulers to maintain social order. So in those days, there was no democracy. Even now, some people shout that there is no democracy. They should go into history and then they will understand what is the lack of democracy. In those days, the social order was maintained at the barrel of the gun, or you can say tip of the sword. So the muscle power was the ruling power, and it was then held by the religion and so on. So in this form of science, that God has created this universe, and only religious people have understood the universe. And the other people, they have not understood it, and if they question, then they are questioning the God. So any questioning was amounted to defying God. That was the sort of situation some 300 years back. And then this pseudoscience was based mostly on hypotheses. These hypotheses were not tested, but these were speculations rather than the experimentation. We find many such hypotheses in history of science. It's very interesting if you go through history of sciences. So there are many such examples which I can quote. For example, in religious books, it was written that how birds are created, how fish created, how insects are created. Then even in Christianity, there is Genesis. In Genesis, it is written how the earth and the life on the earth came into being. In all religions, there are some theories given. For example, it was said that if a tree is on the bank of a river or a bank of a lake, and the leaves of the tree fall, if these leaves fall in water, then fish are born. If leaves are airborne, then birds are born. That was the theory. Similarly, if you look at the periodic table, then what is the symbol for gold? Symbol for gold is Orium. Why it is called Orium? Orium means sun, and sun looks yellow. Gold is also yellow. So there was a hypothesis. Why sun is yellow? Because there is huge amount of gold inside the sun. So this was stated by the religious people, and I mean the priest, the chief of the religion. And you are not supposed to question that. If you question that, it means you are against the religion, you are against the king, you are against the society, you have no right to live. You are danger to the society. So anybody raising the question, he will be just eliminated. That kind of science existed in those days. You might be knowing the story of Copernicus. He said that the earth is moving around the sun. In fact, such observations come from the observation of stars. But it was written in the religious book that earth is stationary. What is the logic for stationary earth? It was said that man
हाँ
is
बोलो.
most precious creation of God. Who would not like to? Who would like to oppose that? You will also be pleased, isn't it? If you are said that you are most important in this animal world, you will feel very happy. Yes, I am very important. I am most gifted creation by the God. It satisfies your ego. And where does this human population live? It lives on Earth. So Earth is most important place in the universe. No questioning that. It is just hypothesis. And if Earth is most important, then it will not move. If Earth moves, what will happen? Then all of us will be unsafe. So Earth doesn't move. It is the sun, it is the planets, they move around the Earth, but Earth is stationary. And when scientists said that no, my dear, Earth is moving around the sun, then he was treated as a traitor. So scientists who challenged the ideas of religions, they were sort of denounced, they were called as traitor, they were called as enemies of humanity, and they were sentenced to death. So it was very difficult to do science in those days. In fact, it was very difficult to study anatomy in these days. How can you see inside a human body? So only way to see inside human body is there were no instruments in those days, no laparoscopy, nothing. So only if you cut open a body, then only you can see what is inside the body. But you can't cut open a living person. So the only thing is that if there is a dead body, then you can cut it and see inside and so on. But this was forbidden by the religion. They were very much afraid there will be ghost. So if you tamper with the dead body, then there will be a ghost. There will, so this was a fear of unknown, and it was not allowed to study anatomy. So scientists had to face such odds, such obstacles in arriving at the truth. Now imagine, I mean, see how lucky you are. You can study science, you can question, you can verify. So you don't have to just accept whatever is written in the book. whatever is told to by your teacher, but you can verify it in the laboratory and be satisfied, and then only you accept it as a truth. So, this was the structure of the pseudoscience some 300, 400 years back. So, such a rigid structure, and this brought a bad name to science. So, slowly in modern science, people gathered, and as slowly civilization developed, and we became more and more democratic, more and more patient, and started listening to others. Then the science developed, the real science developed. So the black side of the pseudoscience we wanted to get rid of, and we say in modern science all the bad points of the history, these we tried to remove. So modern science is designed to remove these lacunae, and hence the structure of the science which we saw earlier, that science is objective. It doesn't depend on who is saying that. However big name a scientist might be, but he has to prove whatever hypothesis he forwards. So it is then the objective description, then establishing cause and effect sequence either through these observations or through the experiments in the laboratory, then only it will be established. Then making predictions, so how right you are, then these predictions will be verified again. So the modern science moves through these steps and we get laws of science. So this is science then. So there are two basic principles of science. One is principle of causality and principle of determinism, or what we call as certainty. So the objective of science was from moving from uncertainty of the pseudoscience to the certainty of the science. So what is principle of causality? The principle of causality is that there is no effect without a cause. There is nothing like miracle. Nothing happens of its own. But there is a cause behind every effect. So if it rains, you know that there are clouds. And a definite cause will produce definite effect. So these are two basic principles of science which endows it with something definiteness or the certainty. So from the darkness of uncertainty, the science takes you to the certainty, the light of certainty. So what a structure we have seen. So in physics, branch of mechanics, mechanics was the first branch which was put on such solid foundations. Now what is mechanics? Basically, in mechanics, we define certain quantity and we try to understand the motion of objects in terms of cause and effects. And since physics is a science of measurement, the cause and effect must be in terms of quantity, definite measurement, not qualitative. So various laws of physics thus can be written with the help of a mathematical equation, because cause you will put in one side of the equation and effect will be put on the second side of the equation. For example, you write Ohm's law as, say, V equal to IR. V is the voltage. So if you apply certain voltage to a resistance, then the ratio of voltage to the current is always constant characteristic of that body. We call it as resistance of that body. So this is definite. We can write. So mathematical equations, they are sort of shorthand notation for writing the law of physics. But remember, The equation themselves are not laws, because equation itself does not tell you which is the cause and which is the effect. Hence, we must write the law in form of statement. So if you say that I ask you a question, what is Newton's law? And you say P equal to mf, then that is not correct, because it doesn't tell you what is the cause and what is the effect. Hence, we write it in statement form that a body continues its straight line uniform motion unless acted upon by external force. So, this is the statement of the law. But as a shorthand, can write it, right? That when external force is applied, then ratio of force to the acceleration is constant, and it is called as then the mass of the body. So many a times even scientists forget this thing and we misinterpret the equation. So we have to understand what is cause, what is effect. Then objectivity demands that the laws of physics must be universal. They do not depend on space and time, right? So if you are learning some physics in school, same laws of physics will hold in Ramdev Baba College of Engineering also. If Newton's law tells you that the ratio of force to acceleration is mass of the body, if this is true on Monday, it will be true from Monday to Sunday, it will be true 24 by 7, it will be true everywhere. So the laws of physics are such that they are universal. Now we have not proved this, right? But this is the assumption. So again, we will go into this, how correct this is. But our uh, journey from uncertainty to certainty demands that laws of physics should be universal. If certain laws are not universal, then they are not accurate. We must modify them. Modification is allowed. If we find some deviation, then we will modify the law. So classical physics thus is the description of the universe and its understanding in terms of cause and effects, or as I mentioned, the principle of causality and principle of determinism. That's what we mean by certainty, that there is no effect without cause and definite cause will produce definite effect. So the Newtonian laws describe mechanics in terms of cause and effect. Now you have to remember momentum is the cause and velocity is the effect. Force is the cause and acceleration is the effect, and so on. It took quite some time. So scientists before Newton, they could not ascertain as to what is the cause and what is the effect of force. For some 100 years, scientists thought that the effect of force is velocity. This is wrong. Why do the object has velocity? Velocity is because of momentum. You do not need any force for velocity. Velocity is by virtue of momentum. Why an object is moving? Object is moving because it possesses momentum. Then what is the cause by force? Force changes this momentum. Rate of change of momentum is equal to applied force. And this produces acceleration. If there is no force, then motion of the object is unaccelerated and so on. So all entire mechanics can be derived on basis of Newtonian laws. So the interaction between the two objects, I mean, what causes the force, right? Why there is force? What is the force which two bodies exert on each other? This force we call as the gravitation. And then this was given by the inverse square law. The forces two bodies exert on each other is proportional to product of their masses and inversely proportional to distance between two bodies. F is equal to G into M1 M2 by R square. G is called as the constant, gravitational constant. And this is universal law. M1, M2 might be anything, R might be anything, but this law will be observed. So whether this is the force of gravitation between tiny objects or whether it is the force between very massive objects like sun and earth and so on, you can explain entire planetary motion on basis of this law. And you can also explain motion of a pendulum also on such type of laws. So the laws of mechanics are universal. They are valid everywhere, they are valid at all times. So this is what we wanted, from uncertainty to certainty. So this was established first in mechanics. And also it was developed, mathematics of this was developed, so it was more convenient instead of working with forces to work with potential. Force was explained as gradient of potential, so that made mathematical modeling of all these things more convenient. And then you could apply another contribution of Newton, uh, that was also the calculus. So you could apply the differential calculus and integral calculus very conveniently when force is expressed as a gradient of a potential. So far so good. This is about the mechanics and this is about the force of gravitation. But is this the only force existing in the nature? You know that even in our common everyday experience, that if you just comb your hair and if you hold this comb to the paper, then paper gets attracted. It moves against the force of gravity. So we know that there are other forces also. Gravitational force is not the only force. There are other forces existing in nature. So other branches of physics, these were considered, like for example, electricity, just what I told about you, that the piece of paper being attracted by the comb. So this is the static electricity. Then we have got magnetism. We know that certain objects are magnetic. So if you take a magnet and keep it suspended, then it will move towards the south north direction. It will align itself parallel to north south. So there are forces which are due to magnetism, forces due to electricity, and so on. So again, the branches electricity, magnetism, these were also developed. Understanding was developed in terms of cause and effect. What causes that paper to move towards comb? What causes the magnet to align itself parallel to north-south direction? This was understood. So, it was again written in language of mechanics. For example, we start with potential, isn't it? What is the definition of gravitational potential? It is work done in bringing unit mass from infinity to that point. This was called as the potential. Then in electrostatics, we define electrostatic potential. Language is same. So electrostatic potential is work done in bringing unit positive charge from infinity to that point. This is called as the electrostatic potential. In magnetism also, again we have similar definition. Work done in bringing unit north pole from infinity to the given point is called as the magnetic potential. So the advantage is that we could describe now the electrostatics, magnetism also in a causal and deterministic way. So nothing is uncertain about this. And even these laws were inverse pair laws. For example, forces two charges exert on each other. They are proportional to the product of charges and inversely proportional to the square of the distance between two. So we have got the gravitation law, F is equal to G into M1 M2 upon R square. Here force is equal to proportional to Q1 Q2 upon R square. There is small difference. In case of gravitational constant, it is universal. Whereas in this case, the constant of proportionality depends on the medium. So we call it as, say, dielectric constant, dielectric permittivity of the medium, and so on. Similarly, for magnetism, the forces exerted by two unit poles or two poles, magnetic poles, they are proportional to the product of that and they are inversely proportional to the distance between them. So in this way, we have laid the foundations of physics. We have got the uh, mechanics, we have got the electrostatics, we have got the magnetism. All this could be described in causal and deterministic way. So we had the science, which was totally certain, anybody could verify it. So these are my laws of physics and so on. So you know, this deterministic distribution is in terms of observable. You don't have to accept my word, but I am writing in terms of some quantity. You can measure the magnetism, you can measure the charges, you can measure the distance, you can measure the force, you can verify that F is equal to G into M1 M2 upon R square. So this is totally the deterministic description. Similarly, this description is based on some fundamental concepts like absolute time and absolute space. So only assumption I am making is that all the quantities I am writing in the equation, they are experimentally measurable with infinite accuracy. Now this sounds fair enough that okay, length of an object, I can measure it. I have got a measuring tape and there are marks, of millimeter. So I can measure it within 1 millimeter. If I want better accuracy, I will take vernier caliper. I can measure even zero point 0.1 millimeter. Then I can have another instrument. I can measure it up to 0.01 millimeter. So only I have to get a proper instrument for measurement. I can measure an object, right? I can choose some wavelength of light. I can choose interferometer and I can measure it within, say, some 10 raised to minus 5 centimeters. So I can reach any accuracy and I can measure it, provided I construct an instrument, an apparatus for measurement. So this is a postulate that everything can be measured, whatever certainty you want, you can measure it. Only you have to construct an apparatus for that. But basically, nature is definite and we can measure it. In mathematical terms, this classical physics is Galilean invariant. Anyway, I'll skip it. So in this description, the universe is also divided in terms of matter and radiation, right? So everything could not be described as a particle or something, but there are some waves also. I find that light, yes, light is moving in terms of wave, and these waves, they can also deposit energy, and particle also can transfer energy by collision, whereas the waves can be absorbed and they can transfer the energy through radiation. So these particle and wave descriptions, they became mutually exclusive. It means if something is particle, it is not a wave. And if something is wave, it is not a particle. For example, particle has got definite position. Two particles cannot occupy same position in the space. In simple words, two particles cannot overlap. But waves can overlap. I know waves can overlap and we can see interference. We can see diffraction. So two waves can overlap, but particles cannot overlap. So what is a wave? Wave is, after all, some periodic change in the observable, and the changes propagate with definite speed in the space. That is a wave. For example, what is a sound wave? Sound wave is periodic oscillation of medium particle from the equilibrium position. And then this motion imparts from one particle to the other particle and the wave propagates. What is light wave? Light wave is oscillatory electromagnetic fields, and these fields propagate in space. So I have very clear certain idea that what is wave, what is particle. Particle have got momentum. Particle can transfer momentum by collision, whereas waves have got different way, isn't it? Energy of the wave is proportional to its amplitude. Whereas I know that the momentum, of a particle is given by its mass into velocity. Wave, waves do not have mass, and so on and so forth. So I have got very clear cut certain description of classical physics. So all the characteristics which we have discussed up till now, this became part of definition of physics, and we call this as classical physics. Now it will become clear when we move to the next part. So, towards end of 19th century, it was thought that our understanding of universe is complete. And we have understood all the physics. We are much different now from the pseudoscience. And in future, what will happen? We may measure accurately, more accurately. That is all. If I have determined value of G as say 9.8 meters per second square, then somebody will determine 9.81 or 9.814 and so on to nth decimal places. But basically, it is the force due to acceleration due to gravity. Ironically, when scientists were contained and they were satisfied that nothing important is to be discovered, most important discoveries were made towards the end of the century, and it shook foundation of physics, and it again asked the same question that whatever you have stated, is it definite, is it really certain? So all our fundamentals were again questioned. So we'll go into a brief history of that. So drastic revision of basic concepts was needed, for understanding these experimental results. So the concept of principle of causality, principle of determinism, the certainty, and so on, the time, definition of space, or rather the invariance of time and space, all these fundamentals were challenged, these were questioned due to new observations. So let us go into these new observations. And these observations were explained in terms of relativistic mechanics and quantum mechanics. These are two branches of modern physics. Some part quantum mechanics you will learn this year. Some is already taught to you in rather ad hoc way. So classical physics failed to explain many experimental results. So your theory is correct if it explains all the experimental results. Otherwise, it is wrong or at least inaccurate, and you have to modify. So what are these results which could not be explained? So I can just briefly summarize them. One was the black body radiation. Another was structure of atom and atomic spectra. Then the photoelectric effect, electron diffraction. So basically, these four experiments, could not be explained by classical mechanics. So first we come to black body radiation. What is black body radiation? When a body is heated, it is at certain temperature, then it radiates energy. I told you in the beginning, isn't it, that universe was divided in classical physics in terms of matter and radiation. So everything is either matter or it is radiation. If it is matter, it is not radiation. If it is radiation, it is not matter. So when object is heated, then it emits radiation. These radiations are called as black body radiation. And then there are certain laws of that. You might be conversant with those laws. For example, the Stephen Boltzmann law or the VS law and so on. So what it means is that higher the temperature, then the intensity of this radiation is more. If you plot a graph of intensity versus wavelength, then you will get a typical curve. And as the temperature increases, the maximum in this curve will shift to shorter and shorter wavelength. But when the theory was classical theory was applied, then the predictions of theory, these were different. The theory predicted that the intensity will go on increasing with the drop in wavelength or increase in the frequency of the radiation. This was called as ultraviolet catastrophe, whereas such a graph was not observed. The graph was in fact more or less like, say, Maxwell-Boltzmann type distribution. Not exactly symmetry, but somewhat akin to that. And then this was very peculiar. Your theory could not explain. At that time, then Planck made a very peculiar assumption. He said, no, if you take the classical physics derivation, that energy of radiation is proportional to amplitude square, then we cannot explain the experimental results. He made an assumption that energy is in multiple of quanta. So he introduced the word quantum. Quantum means it's a unit. It's a small measurement unit. So the energy that a body radiates is in multiple of h nu, where h is the Planck's constant, nu is the frequency of radiation. He made that assumption and then he could explain black body radiation. So black body radiation was explained, but the assumption was that energy is h nu. No reason why it is E is equal to h nu. No reason. Classical theory says E is equal to amplitude square. E does not depend on frequency. But Planck made assumption E is in multiple of h nu and he could explain everything. Next was structure of atom. You may be acquainted with some of these terms, nucleus and so on. So you know that atom consists of nucleus and electrons moving around nucleus. How come we come to this, say, Rutherford picture of atom? This came from the experiments of scattering of alpha particles. You know, alpha particles were discovered and they were found to be positively charged. When these alpha particles were scattered, it was found that they were scattered from very small portion of atom. So they were rather, repelled from central portion of the atom. And repulsion we know, like charges repel. So if alpha particles are repelled, positive charges, it means atom also must contain some positive charge. We know two positive charges will repel each other. This is the law of electrostatics. And the force also we know, force with which they will repel each other is Q1, Q2 upon R square. We know the law. Hence, there must be positive charge. But atom is electrically neutral. So to balance that positive charge, to maintain the charge neutrality, atom must consist of positive charge and negative charge. But if it contains positive charge and negative charge, I know electrostatic, that two positive charge and negative charge will attract each other. And I can do it with gold leaf electroscope, that I can in fact cancel the charges. Positive charge will cancel with the negative charge. Then how the charges remain separate in an atom? You have got positively charged nucleus and negatively charged electron, but they remain. They do not, their charges do not cancel. So how to explain this paradox? Then a sort of, planetary picture of atom, model of atom was given. We know that we have got Earth and we have got Sun, and Earth is moving around the Sun. And what is the force of attraction between Earth and Sun? G into m1 m2 upon r square. So many times I ask this simple question, that Earth, there is force between Earth and Sun. Then why Earth is not pulled into Sun? Why Earth doesn't fall into Sun? Of course, it doesn't fall. We know that's why we are alive here. We are alive here to discuss physics. The reason is that Earth is in a orbital motion. So there is a angular momentum, isn't it? So there is momentum, angular momentum, and then we know there is a centripetal force of attraction, and there is also centrifugal force, and these forces balance. So we know that this force due to this orbital motion, this balances the force due to attraction, and at such distance, Earth is in the orbit. So same logic was applied, that electrons are in the orbit, so they will have angular momentum, and this balances the force of attraction, rather the electrostatic force of attraction between the positively charged nucleus and negatively charged electron. But this argument did not work here. You know, the reason is that Earth can remain in the orbit without losing energy, and the situation can continue indefinitely. On the other hand, if charge is accelerated, then it emits radiation. If it emits radiation, then it loses energy. If it loses energy, then orbit shrinks. And if orbit shrinks, electrons should fall into nucleus. So stability of atom could not be explained by classical physics. But atom is stable, we know. Atom is stable, that's why this universe is in the existence. That's why you and me, we are talking, we are living, we are made up of these atoms, and atoms are stable. So this could not be explained. At the same time, it was found that if these atoms are excited, for example, if the if you take sodium chloride and put it in the flame, then the flame becomes yellowish. So whenever these atoms were excited, they emitted light. But now this light was not like black body radiation, but light was only of specific frequency. Sodium vapor lamp, it emits at 5889 and 5896 angstrom. So why does it emit only at those wavelengths? And when it is not excited, it does not emit, atom is stationary. No explanation is possible with classical physics. At this time, Niels Bohr made certain postulates. You might be acquainted with Bohr's theory. He started with Planck's idea that E is equal to h nu. Then he made the assumption that atoms, electrons move in certain orbits, which he called as stationary orbits, without radiating. And when they change from one orbit to the other orbit, then the difference of the energy is gives the light, and frequency of light is given by E equal to h nu, same Planck's formula. But again, this is just an assumption. Why, how can electron move without radiating energy? How can that orbit be stationary? It doesn't happen anywhere. Outside the atom, if there is accelerated electron, it produces electromagnetic radiation. So you could not explain this. So this was all ad hoc, Bohr's theory. So it is like, peeping at the answer pages. Means you are not solving the problem, you are unable to solve the problem. So you look at the answer and then you work your way back and write some hodgepodge steps and say, I have solved the problem. This is not fair. So Neil Bohr had not done a fair thing in the sense that this was not the final solution of the problem, but he only showed a way that if somehow we can make these orbits, certain orbits stationary, then the difference of the energy that explains the emission of light or the atomic spectra. So somehow you can explain the stationary orbits, you can also explain the spectra. Another interesting experiment was photoelectric effect. So you might be conversant, or this year you might be performing this effect. What is photoelectric effect? If light is falling on the material, certain materials, photosensitive materials, then this light is absorbed and electron is ejected. This gives photocurrent. And a peculiar thing is that not all the light, not light of any wavelength can produce photoelectric effect, but there is existence of threshold wavelength. So wavelengths shorter than that, they can only produce photoelectric effect. Wavelengths longer than that, they do not produce photocurrent. Now if you come to classical theory, light is a wave and energy of wave is proportional to the amplitude. So if the amplitude of the wave absorbed is such that energy is greater than the binding force between the electron and the solid, then electron will be ejected out. So this photoelectric effect should depend only on the intensity of light and it should not depend on the frequency of light. So that is the prediction of classical physics, but experimental results are opposite. So at this time, Einstein then gave the explanation. Again, this was ad hoc explanation. Einstein said he assumed that light is not a wave, but light is a particle. And we know the collision between the two particles. A particle can give how much energy, how much momentum can be transferred. It can transfer entire or only part of its momentum to the another particle with which it is colliding. And he said the energy or the momentum of the particle is h nu by c. So where nu is the frequency. So h nu by c is the momentum, or h nu is the energy. So energy of the particle, rather light, is not proportional to amplitude square. Again, same Planck's assumption, E is equal to h nu. So if this h nu is greater than the binding energy or work function of that material phi, then h nu is equal to phi plus half mv square, where v is the velocity of electron. So it can explain. So whenever h nu is less than phi, no photoelectric photocurrent will be observed. Whatever might be the intensity, so energy is not proportional to amplitude square, but energy is in only h nu. So here light has to be treated like a particle and not as a wave. But if it is a particle, how it can produce interference? Particle has got definite position. It cannot give you interference bands. It cannot be present simultaneously at two positions, right? So you do some tricks with the communication technology and you are present, I know, at two places simultaneously. You may be signed in here in the lecture and going and enjoying with your friends outside also. That is quite possible, I know. But a classical particle, it cannot be at two places simultaneously. So a particle cannot produce interference. On the other hand, light produces interference. So light is a wave. But if light is a wave, then how can it produce photoelectric effect? Light must be particle in order to produce photoelectric effect. Much later, another experiment was performed in which electron produced diffraction. We know electron is a particle. In CRO, we see electron produces bright spot, electron has got definite position. I can calculate trajectory of electron, right? It moves in a parabola. If I apply a voltage to the deflecting plate, then the path of electron is parabola. Electron is a particle. If it is a particle, how can it produce diffraction? So in some experiment, electron is behaving like a wave. In some experiment, electron is behaving like a particle. Similarly, in some experiment like interference, light is a wave. In another experiment, photoelectric effect, light is behaving like a particle. So is your physics certain? Have we moved from uncertainty to certainty? Your physics is not certain. Your classical physics is not certain. You cannot answer the question. Simple question, is light wave or is light particle? This is paradox. If you say light is a particle, then how it can interfere? If you say light is light is a wave, then how it can produce photoelectric effect? So it is this lose-lose situation. We want win-win situation. This is lose-lose situation. Whatever reply you give, you are wrong. So this is very, very, rather enormous situation before scientists, that all their answers are wrong. That light, you say it is wave, you are wrong. You say light is particle, again you are wrong. So how to obtain the answer to this question? Now these questions were answered by quantum mechanics. So this is what we call as now old quantum mechanics or ad hoc quantum mechanics, that you assume E equal to h nu. Why you assume? You don't know. It is like pseudoscience, that God has said. God has said this. So your answer is Max Planck has said that. No other answer. Electron is stationary in orbit. Why? Because Bohr has said that. Is this science? This was not science. So the science was then supplied by quantum mechanics. De Broglie suggested first this idea that our description of universe is not correct. The classical description is not correct. We have divided universe between wave and particle. This is not correct. But all entities have got dual nature. They can be like waves and they can also be like particles. And what is the bridge between the wave property and the particle property? Particle means momentum. Wave means wavelength. Then lambda is equal to hp, where h is again Planck's constant. So this is the relation. This is the bridge between the particle picture and the wave picture. This hypothesis was suggested by Louis de Broglie. There was another solution given, and this was operator mechanics. This was totally mathematical solution. So this sort of operator mechanics, what does it say? It is very abstract. It says that physical quantities, they are not represented by some observable, some units, but they are represented by mathematical operators. Then there was matrix mechanics. So this was also a solution. They say that physical quantities are not represented by observables, but they are represented by certain matrices. Then you perform some mathematical operations and then you come with certain predictions. Now the modern quantum mechanics, is actually palatable mixture of this wave mechanics, the operator mechanics, and the matrix mechanics. And we interchangeably use all these languages. So this is quantum mechanics. Now basically what does it say? So the experimental results which could not be explained by classical physics, but this could be explained by some ad hoc idea. This gave one clue that mutually exclusive description of particle and wave is wrong. Wave particle dualism has to be incorporated in your theory. Now, how to incorporate it? The root cause of this is deterministic description, certain description in terms of observable. We have made an assumption in classical physics that I will write the equation force is equal to m1 m2 upon r square, and I say force can be measured Distance can be measured with infinite accuracy. This is just an assumption. Quantum mechanics says that this assumption is wrong, that physical quantities cannot be measured with infinite accuracy. But there is some limit to this accuracy. And then this limit, you might have learned about the Heisenberg's uncertainty relation, that the accuracy is not infinite, accuracy is finite, or the uncertainty product delta x delta p, this cannot be less than the Planck's constant. Delta x delta p greater than equal to Planck's constant. This is the uncertainty principle. So this is now the law of new physics, or the law of quantum mechanics. And this quantum description, this is in terms of wave function. It is not a physical observable. Now this produces, there are lots of questions. Our classical description is in terms of physical observable. Why it was in terms of physical observable? Because it must be objective description. So if something cannot be measured, how can I say your description is correct or description is wrong? It must be measurable. But in quantum mechanics, the description is in terms of wave function. Wave function cannot be measured. It is not a physical observable. But you can have physical observables from the description in probabilistic way. So the information from this wave function can be obtained using the operators, and this information is in general probabilistic. So it is as much causal and deterministic as permitted by uncertainty relation. So it is not infinitely certain, but it is as much certain as allowed by Heisenberg's uncertainty relation. So in a way, we have completed the circle. The pseudoscientists started with uncertainty. They said these are some rules by God, you should not question it. Then we came to the classical physics. And what did classical physics say? The laws are certain and they are, you can measure them, you can verify them, you can question them, and so on. And now in quantum mechanics, again we say that, well, measurements are not with infinite accuracy as assumed by classical physics. But whatever instruments you invent, you cannot measure the physical observables beyond certain level of accuracy. And there will be some uncertainty in measurement. Delta x delta p, you can never make it less than h cross. This is the limitation of nature. This is how nature exists. This is how universe exists. So it was very difficult to digest all these ideas, because with great difficulties, with great opposition from the politicians and religious leaders, we developed classical physics. From the rules of Bible and Ved and all these religious books, we developed laws of science. And we say these laws of science are universal. So you can test it, you can check them, and you don't have to accept my word for it. Now you have gone back and you say, no, it is the Heisenberg's uncertainty relation. Have you proved it? Indirect evidence. And all your sense for, logic tells you, no, classical physics must be correct. If a particle has got a position, why cannot I measure the position with infinite accuracy? What prevents me? That was the question. Why I should measure it in a probabilistic way? Probability, when do we use probability? Probability is a measure of ignorance. So if I do not know something certainly, then I will say, okay, probably, because I'm not certain about that. So it is a measure of ignorance. So even Einstein did not believe in quantum mechanics. He said God has created the universe, and this universe is run by definite laws. So I must be able to find these laws, I must be able to measure it. Now, if this is true, Einstein has said he does not play dice. What does it mean? It means that God has created universe. Universe is run by definite rules, so nothing should be left to probability. I should have as definite laws as in classical physics. So this uncertainty principle, this doesn't, meet my demand of uh, perfect science. This was the view of Einstein. But our science is not subjective, it is totally objective, and we go by the experimental results. So, all experimental results are explained by quantum mechanics, hence, quantum mechanics must be correct. We have not come across any contradiction to this up till now. So, the principle of, say, uncertainty principle, this must be correct. Then what happens to principle of causality and principle of determinism? Then principle of causality and principle of determinism is there, but it applies to wave function. We will say a wave function will not change unless there is a cause. So principle of causality. A wave function, definite cause will lead to definite change in wave function. So principle of causality and principle of determinism is valid in quantum mechanics also. However, wave function itself is not a physical observable. So we say principle of and causality and principle of determinism, they are not applied to the physical observables, but they are applied to the wave function. And from wave function, we have to find out the physical observable. The only way we can obtain physical observable from wave function is a probabilistic way. It means two physical observables which form canonically conjugate pairs cannot be measured with 100% certainty, but there is some uncertainty. Now that doesn't mean that everything is uncertain. Uncertainty is between the limits of delta x delta p is equal to h cross. That is very small quantity. Tomorrow if you perform some experiment and teacher tells you that no, your value is wrong, you have obtained value of g as 15 but g is 9.8, you shouldn't come with the answer, sir, there is some uncertainty. So how much is the uncertainty, that also we should know, right? So uncertainty is not what you imagine or what many scientists portray, that this is all uncertain and quantum mechanics is wrong and so on. No. How much is the uncertainty? Uncertainty product delta is delta p. This is of the order of h cross. So we have not moved, as the title goes, from uncertainty to uncertainty. So at the beginning, there was huge uncertainty. There was no science. We have at the whim of the people that somebody has said this law, you cannot question it. So this was really uncertain. Really, you didn't know how the origin of life, you didn't know. But if somebody has said that fish are born in when leaves fall in water, okay, you have to accept. Uncertain, everything uncertain. From that, we have moved to everything certain in classical physics. Now, there is some element of uncertainty, but this uncertainty is not infinite. This uncertainty is only that much as given by Heisenberg's uncertainty relation. And why it is there? Why does it exist? It exists because of our description of classical physics. It is not totally wrong, but it is approximate. We have assumed that everything can be measured with infinite accuracy. That assumption is wrong. So there is limit to everything. So there is a great lesson to this for scientists and for everyone, that yes, we must keep our sense of logic alive. We must at every stage examine the statements, examine the results, and then only we will arrive at the truth. After all, the purpose of science is to arrive at the truth. That is the objective of the science. So, in this short time, I have taken you to this journey from uncertainty to certainty. Now, I am not certain how many of you were really listening to this and were awake throughout this journey. So, I will be finishing my talk now. So, it's a time to wake up to the reality. And thank you very much for listening. So, I hand you over back to Dr. Khushbu Sharma.
Thank you, sir. I now request all the participants, students, to post their questions. Sir will answer those questions. Student, please post your questions.
So I only see the message, thank you, sir. So I don't know whether these thanks are for ending the lecture or whether they have enjoyed it. I don't know. But I hope to have more interaction with students. Yeah. There is some question. What effect does Hermitian operator have on a unitary matrix? Now, this is a rather, sort of mathematical type of question, that as to what does an Hermitian operator do. So, a Hermitian operator will obviously, take one matrix to the other matrix, and the multiplier will be a real number. So, if the eigenvalues are real, then we call the operator as the Hermitian operator. But that is again true only if the basis is orthonormal. So I assume that you are meaning the orthonormal basis and so on. I really, doubt also whether you have learned that much quantum mechanics up to 12th or not. So all these questions, of course, we can take up when we go through the course. Yeah, another question asked by Priyanshu Korekar is it possible to measure the velocity and mass of a particle at a time? So yes, mass and velocity, these are not canonical conjugate. So there are, in classical physics, we define some canonical conjugate. For example, if there is energy, then conjugate coordinate to that is the time. So time and energy cannot be measured simultaneously. Similarly, position and momentum cannot be measured simultaneously. Yes, how science and spirituality are interlinked with each other. Interesting question. Again, it is in realm of perhaps philosophy. So, science believes that we still, explain the origin of universe in terms of laws of physics. But if I explain this, there is always a question: who created this? Who created this? Who created? And then there is no final answer to that. So, what science says is that God has created universe. God has created laws of physics. For example, if you say why there is inverse square law, then God has created that. Why velocity of light is 3 into 10 raised to 10 centimeters per second square? Well, God has created. God has set the rules. But once God has created the rules, He is not playing with those rules. He has left the universe to run itself by those rules. Beyond that, God is not playing a role. God is not making you, successful in the exam or failing you. So it is only up to your hard work and so on. So the science acknowledges presence of God. It has to acknowledge there is something which created the universe, but universe is run by the rules created by the God and nothing beyond that. So that is the just how it stands. Many questions similar. Can you explain once more why Einstein did not believe Heisenberg's uncertainty relation? I tried to explain that earlier. You know, in classical physics, we said that everything can be measured. It applies to your sense of logic, isn't it? For example, if I'm measuring your height, I take a tape and I find that you are 1.72 meters tall. If I take a vernier, I can measure it 1.721. If I take wavelength, I can measure it within 10 raised to 5 minus 5 centimeters. So it applies. I mean, if you go on extending that, if you are real, your height is a real physical observable, it should be measurable with any certainty. Why should there be any uncertainty? This doesn't apply, appeal to your sense of logic, that why should there be uncertainty? God has created this universe. Universe is run by the definite laws of physics, definite laws God has created. Then everything must be measurable. God has not left anything to probability. So he said God doesn't play dice. It means universal rather, is universe is run by definite laws. So everything should be measurable. If I am not able to measure, it is my inability. But what does quantum mechanics say? It says it is not my inability, but system exists like that. That is why sometimes I find that properties can be explained in photoelectric effect, that particle is, electron is, or rather light is a particle. And in interference, light is a wave. The reason is that light is neither a wave nor a particle. My description was wrong. And why that description was wrong? Because I was trying to find out position also and momentum also at the same time. This is impossible. Because this is not possible, I was running into wrong answer. But Einstein believed that his theory of relativity will provide correct deterministic answer. And he thought that quantum mechanics was wrong. But as the experiments later on proved that we need both theory of relativity and quantum mechanics to explain this universe. Now, interesting question by Shivam Singh, that someone is faster than speed of light, then he could eventually build the time machine. It means both things are impossible. That you cannot build time machine and you cannot have speed greater than the speed of light, because mass of the particle is related to the rest mass. So m is equal to m0 upon under root 1 minus v square by c square. So if v is greater than c, it means mass will be negative. So if mass is imaginary, how can that particle exist? So these are just particle in abstract space. People call them as tachyons and so on and so forth. So another interpretation is that that particle cannot be brought to a state of rest in any frame of reference. So very interesting, questions. I'm very glad if you are thinking of these questions and so on. So someday we should also talk about the theory of relativity. It is, very important landmark in history of physics. It's a pity that theory of relativity is not discussed at any level in schools or in the graduation or post graduation. So again, many questions there seem to be on the cosmology and the relativity, because this cosmology, the origin of universe, this cannot be explained by quantum mechanics only and relativity only, but we have to integrate the theory of relativity and quantum mechanics. Then only we can explain. Now, another interesting question is by Tushar Raute. What quantum mechanics and consciousness have in common? I don't think there is in common, because physics is science of measurement. So physics will always talk about observables. Even in quantum mechanics, though we work with wave function, which is not physical observable, but in the end, we make predictions from the wave functions and we come to some observable. These observables, we tally the results and then only we accept quantum mechanics. Now, if we talk about quantum mechanics and consciousness and mind and so on, then this is not physics, because mind is not measurable. So it cannot be measured, and physics is science of measurement. So mind, etc. These things, we talk in different. Maybe it will come under psychology and so on, but it is not part of physics.
Sir, there are so many questions.
Yeah.
So, students, you can contact Professor Moharil and posting his email address. So
Yeah.
if you want to,
perhaps we can have some forum. We can have some forum where we can club all these questions into categories, and similar questions can be answered once. So I will be very happy to provide, written answers, or if it is offline meeting, then maybe we can have more interactive sessions. I am very glad that they have been there. So now I am certain from uncertainty. At the beginning, there was uncertainty whether I can attract students, whether they will stay awake throughout this lecture. But yes, they had been awake. So very nice. Students, thank you very much. And now I am certain that, okay, my speaking here had some objective. So I'm looking forward to have more interaction with you in future. Thank you.
Now I request Khushbu Sharma ma'am to propose vote of thanks.
Thank you so much, sir, for your wonderful talk. Surely, student will get the elementary idea of the physics and the science. And we are so glad to see the lot of questions and queries the students are having. And definitely, sir, we will try to conduct one forum to answer this question and all type of questions. So, students are now. Thank you so much for being with us and sharing the valuable time with us, sir. Okay, sir. And the students, now we would like to conclude this session, and all of we will have next session at around 2 p.m. sharp. Okay, the link with you, and just join that link, and we will meet at the 2 p.m. Thank you.